So we're moving on to discuss surfaces now, and our goal is to understand how to express surfaces, how to, for example, give parametrization of surfaces. That's not very sophisticated, but it's a bit trickier than just lines. And then we're going to want to know how to calculate the area of a surface, and everything is analogous to what we did with curves. So first we learned how to work with curves, parameterize them. Then we wanted to know how to find the area of a curve. Then the length of a curve, area of a surface. And then we wanted to know how to integrate over curves. And there were two sorts of integrals. There were integrals of scalar functions, and then there were integrals of vector fields. Same thing here. Okay, there are going to be two sorts of surface integrals. We're going to know how to integrate scalar functions and how to integrate vector fields. So, starting from the beginning, what is a surface? So, a surface can be given by the graph of a function. Z equals f of xy. That's one way we've already encountered to describe a surface, right? So if we have a function of two variables, the set of points, the graph of the function is a surface. The set of all the points x, y, z such that z is f of xy, that's a surface. Do you agree? Okay, in general, a surface is a kind of two-dimensional object embedded in three-dimensional space, right? So do you agree that the graph of a function is a surface? Does everybody agree? There was one other way we already encountered surfaces, and that was when we discussed implicit functions. Okay? So, for example, alternatively, a surface can be given by some implicit function or some equation. By some equation or implicit function and in fact, this is how we started out. We discussed surfaces at the very beginning of the course, before we ever discussed functions. And we had, for example, spheres and cylinders and paraboloids and ellipsoids. Remember all those? Those were surfaces. Okay? So in general, and in fact, even before that, planes. Planes are surfaces, right? And a plane is given by some equation with x, y, and z satisfying some condition, some equation. Okay? And in general, the way to write that is f, x, y, z equals 0. Some expression containing x's, y's, and z's. Good? Okay. So that's the other way. And it turns out that the most useful way of expressing a surface, the most practical way, is by a parametrization. And that's what I want to devote time to now. So, finally, we can describe a surface by parametrizing it. There should be a cap on length of words. So what do I mean by parametrization? And this takes a bit of getting used to. So let's recall what we did. Everything we do in the next 10 clips, you have to always compare to the exact same things we did for curves. Okay, that's kind of what you should be thinking all along. So how did we parameterize a curve? A curve was taking was taking a line, t ranging between A and B, right? Taking a segment in the x-axis, or in the t-axis, t ranging from A to B, and somehow embedding it into space as a curve, right? So for a curve, we had a map going from R to R3, for example, if it was a curve in three-dimensional space, taking t and sending it to x of t, y of t, z of t. This was how we parameterized the curve. Remember this? Okay, we took t in some interval a and b, three functions, x, y, and z, and we called this r of t. Right? T was in some interval a, b. Does everybody remember what I'm talking about? Pictorially, how to picture something like this, you should be thinking of taking long piece of hair or string, boing, that's this, and then fitting it in three-dimensional space like that. Every point, every t corresponds to some point x of t, y of t, z of t in space. Okay? How are we going to parameterize a surface? A surface is a two-dimensional object. So in order to parameterize it, we're going to need two parameters. Okay? And what we want to do is, for a surface, think pizza. Why think pizza? I don't know if you've ever been to a pizza shop or a pizza booth or a pizza parlor or whatever you want to call it. But if you've seen how they work back in the kitchen, which is sometimes right in the front. So there's a guy there that has the dough. The dough comes in some form of blob, right? And he straightens out the dough, and he gets some domain, hopefully roundish domain, in the plane. Do you agree? The dough becomes some domain in the plane. Okay? So the domain in the plane has x's and y's. Every point in the dough is now an xy point, right? Then he picks it up. Usually he holds it like this, and he does the following. You can practice it with me. He does the following, and catches it. Usually he catches it, right? Again, he picks it up. It's two-dimensional, and he does this. And when it's sitting up there, right, it's a surface, okay? And how does this surface up here, the dough when it's sitting up there, relate to what was originally on the table before he lifted it up? Well, every point down in the domain, xy, or we're going to call it uv, that's the standard, every point uv down in the domain now corresponds, now lives up here in three-dimensional space at some point x of uv, y of uv, z of uv. Do you see that? Every point down here was thrown up to some point x of uv, y of uv, z of uv. Is that clear? Okay? So this procedure, think pizza, is how we parameterize a curve. And I'm not going to draw pizzas, but in fact I am. So it's a map. Let's go back here. Think pizza. It's going to be a map. A parametrization is a map going from R2 to R3, R2 to R3, taking u's and v's taking points in some domain in R2 and sending them to three-dimensional space to some point x of uv, y of uv, z of uv. Okay? Pictorially, we're taking some domain in R2. This is u and this is v. And we have some domain here. This is the dough sitting on the table. And the pizza guy takes the dough, spins it in space, and what we get, this is the parametrization. What we get in three-dimensional space is we get something that looks like this. Okay, maybe we should indicate that this is three-dimensional. So this is now y, x, and z. And every point uv here, so here's the point u, v. Here's this point. This point can now be found, let's say, somewhere here. This is now the point. I'm starting to imagine all kinds of fish and... No, just kidding. Okay, sorry. X of uv, so we're going to call it r of uv, which is the point x of uv, y of uv, z of uv. Good? Does everybody understand what just happened here? Okay. Now, so maybe I'll write this again here, because we want to work with that. R of uv is the parametrization equals x of uv, y of uv, z of uv, where uv ranges in some domain D in R2. So this is D. Clear? Okay. Let's do an example. Let's move to another board. Suppose we want to parameterize a cone. Okay, so a cone, or a part of a cone. So z equals the root of x squared plus y squared. Do you remember the surfaces from the beginning of this course that we discussed? So this is a cone, right? And if I restrict z between 0 and 1, then what I get is just this, right? The upside down clown hat at the origin. In fact, this is dotted, it goes inside. From 0 to 1. Do you agree? Everybody? Okay, I want to parameterize it. Note that all I'm talking about is the surface. Okay, it should be a bit more like this. I'm not talking about the solid, but only about the surface, the two-dimensional, what you can do with a piece of paper. This is the cone, right? Except it's cut nicely up here. Do you agree? Okay. So this is the surface. I want to parameterize it. How am I going to parameterize it? Parametrization I'm going to take parametrization based on what we called cylindrical coordinates. Okay? So all the points on this cone are of the form, let's call it R of UV. Previously it wasn't UV, it was, we called it, what, rho and theta, I think. Rho and theta, or rho and phi, I don't remember. So it's going to be U cosine V, U sine V, and what is Z going to be? What is the Z component? In cylindrical coordinates, there was a Z here, right? But that wouldn't be a parametrization. Every point in space, in three-dimensional space, is of the form U cosine V, U sine V, and Z, right? That's not what we're looking for. We're only looking for points on the cone. Points on the cone are of the form U cosine V, U sine of V, and the Z has to satisfy this. Okay, so the Z is going to be the root of U cosine V squared plus U sine V squared, which is U squared, the root of that, U. And what are the restrictions? The Z is going to be between 0 and 1, right? So U is going to be between 0 and 1. And the V, which is the angle to the positive x-axis, is going to be between 0 and 2 pi. So points x, y, z of this form, where U and V are restricted in these two intervals, are only the points on this cone. A point out here is not going to be of this form. And any point on the cone is going to be of this form. Is that clear? Now, the distinction between parametrizing a surface and doing what we call change of variables is sometimes something that's a bit confusing. Okay, it's hard to get used to. But the most obvious feature that allows us to distinguish between them is that here there are only two variables. Okay, we're only working with two variables, and you should see that not every point in space is of this form, but only points on the cone. Is this clear? Is it clear what just happened? Okay. So here what I did was I took, in fact, a rectangle in U and V, a rectangle in U and V. That was the dough lying down here, and I wrapped it into this surface. That was the pizza thingy in this case. Okay? Clear? Everybody? Okay. Now, again, the same line of thought throughout all this discussion. Think curves. What did we do with curves? Once we knew how to parameterize a curve, let's look back at the previous board. Once we knew how to parameterize a curve, the next thing was to find the tangent vector. Remember? To a curve. The tangent vector was r prime. For a surface, we're not going to look for the tangent vector. What is the more appropriate analog that we need? The tangent vector, it's not clear what the tangent vector at every point is, because there are many of them. The tangent plane, which can be expressed using the normal vector. Okay, so if we knew what the normal to the surface is at every point, that prescribes the tangent plane at every point. Do you agree? So what we want is the normal to the surface, to the parametrization. And how do we do that? So here's the idea. Here's U and V. These two, this point becomes this point up here on the surface. But I can say more, and let's take some colors here. So again, let's think pizza again. Let's think pizza again. When we took the dough lying down here, and we threw it up in the air, okay? Don't look up. So we threw it up in the air. Do you agree that this parametrization, this sending points UV to points R of UV, was continuous, was smooth? If we had two little dots, suppose you took a little blue pen and drew two little dots very close to each other on the dough on the table, and then you did this, the two little dots, well, they're not going to be here and here anymore. They're going to be up here and up here, but they're not suddenly going to be one here and one here. Do you agree? The distance between them was epsilon. Now it's going to stretch a bit. They may turn a bit, but being close here is going to be close here. Do you agree? If you drew a little plus sign on your dough down at the bottom and then did this, that little plus sign is not suddenly going to become a weird picture up in the air. It's going to be a somewhat tweaked plus sign, but it's still you can still see it up here. Maybe it'll be a bit bigger, maybe the angles are not going to be 90 degrees. Do you agree? Can you see that? So this process is continuous and is smooth. Do you see that? Okay. So when we take these two lines here, the one corresponding to V, let's call it U0 and V0. And we take these two lines here, we're going to see them up here, and we're going to see them like this. This is, let's say, going to be the line corresponding to U0, something like this. Let's make a bold line. Let's remove this. It's in the way. So this is, let's say, going to be the line corresponding to U0, and then there's going to be a line corresponding to V0, which may look something like this. And let's remove this so it doesn't confuse us. Okay, so this is going to be the line corresponding to varying U's, but allowing V0 to be fixed, and this is going to be the line corresponding to varying V's, but allowing U0 to be fixed. Okay, so let's recolor it here. This is the blue, and this is the red. Okay, can you imagine that? So it's not flat anymore. It's not exactly 90 degrees anymore, but that's kind of the picture. And I can say a bit more. So here in blue, I have a tangent line. Okay, and what's the tangent line? Well, what is this blue line? The blue line, let's write it in blue. The blue line corresponds, which did I fix? To fixing V0. Right? The blue line corresponds to a fixed V0. So the blue line, blue's dead. The blue line corresponds to R U V0. This is the blue line. Fixed V0, U varies. Do you agree? Okay, fixed V0, fixed V0, U varies. That's the blue line. So those are the points that are going to be along that blue line. And do you agree that it's a curve? It has only one parameter, U, V0 is fixed. Okay, so it's points of the form x of U, V0, y of U, V0, z of U, V0. Do you agree? Okay, so is a curve. And what's going to be the tangent vector to that curve at this point? It's going to be its derivative, right? So it's going to be R sub U, which is x sub U, y sub U, and z sub u. That's this vector evaluated at u0, v0. Okay, maybe let's add that. Ru at u0, v0, at this point, this is the point corresponding to u0, v0, which is xu at u0, v0, yu at u0, v0, z sub u at u0, v0. This is this tangent vector. Does everybody agree? This is a curve. V0 is just here to confuse us. It's fixed. It's no longer a parameter. The only parameter is u, so it's a curve, and this is the parameter. And the derivative is just take the derivative of each component with respect to that coordinate, to that parameter. Okay? And similarly, r, let's write it in red, so is r of u0, v, that's this red curve, and its tangent line at the point is given by r sub v at u0, v0, which is x sub v at u0, v0, y sub v at u0, v0, and z sub v at u0, v0. And let's replace this is with r the tangent vectors. Do you agree? Once we have these two tangent vectors, we can find the normal. What's the normal going to be? Not the dot product, the cross product, exactly. So the cross product of these two vectors is going to be the normal at this point, which we're going to denote by n. So in blue is what we're going to denote in short Ru, and in red is Rv, and their crossed product is the normal at this point. Does everybody see that? Do you agree? Okay, so n, I'm going to erase this because it's really getting in the way. So that was just this. So n is going to be Ru cross Rv. That's the normal vector to the surface at the point u0, y0. So let's, is this clear? Is the idea clear? Okay. Questions? Okay, so let's write that. Maybe we'll leave this example because we're going to use it again. Let's erase here. So the normal vector, the normal to the surface, S is our surface, the normal to S is given by Ru cross Rv. And you can calculate, of course, its coordinates, right? You can write I, J, K, and then you have X, U, X, U, Y, U, Z, U, and X, V, Y, V, Z, V. And all of this, everything is evaluated at the point U0, V0. Okay, so this is the normal to the surface. Maybe we'll do Yeah, so is this clear? Let's do it. Let's find the normal for the example that we had previously, the cone. Let's do it there. So this is the formula. For the cone, normal. So N equals RU cross RV. So we need to find RU and RV, right? So what was R? This is R. What is RU? RU is, let's write it here. I, J, K. RU is the derivative of the parametrization with respect to the parameter U. So it's cosine V. The derivative of this with respect to U is sine V. And the derivative of this with respect to U is 1. Then the derivatives with respect to V is minus U sine V, U cosine V, and 0. Did everybody follow that? Okay. And now let's find what we get. So in the I direction, I get sine V times 0 minus 1 times U cosine V. So I get U cosine V. Minus, you're right, thanks. Minus. In the J direction, I get cosine V times 0 minus 1 times minus U sine V, so it becomes a plus, but then there's a minus because of the J. So I get again a minus U sine V. And in the K direction, I get U cosine squared minus U sine squared, right? So U cosine squared plus U sine squared is just U. This is the normal vector at every point in this parametrization. Let's write it like this. Good? Everybody? Okay. So, this is how we parameterize a surface. Is this clear? We're going to do more examples as we proceed, but is it clear so far? Okay. I just want to add a comment. So, as we did for curves, remember that a curve can have more than one parametrization. You can obviously parameterize in different ways, different choices. And there was the notion of what is a smooth curve. A smooth curve was a curve for which at every point you had a tangent vector, right? That was a smooth curve. And the way we expressed that is we said that there exists a parametrization for which r prime of t, the tangent vector, is non-zero at every point, okay? So it's going to be similar here. A surface is said to be smooth if it has a parametrization, one parametrization, which is C1, so all the partial derivatives are continuous of r with respect to u and with respect to v, and such that the normal is never 0. So there is, in fact, a tangent plane at every point, and such that Ru cross Rv is not equal 0 at any point. So this is what we call a smooth surface, and usually we're going to be working with surfaces like this. Is the surface in our example smooth? That cone? No. Right. Where is it not smooth? Where it's sharp and prickly at that origin, right? So the tip of the clown hat, or the upside down clown hat, is not a point where you can say this. Let's see that this indeed vanishes there. Let's go back to the example. So this is the point where it's obviously not smooth, right? So this is the point which corresponds to u equals 0 and v equals 0, right? And when u equals 0 and v equals 0, we get the normal vector to be the 0 vector. So there is no well-defined normal vector, and therefore there is no well-defined tangent plane here. Do you agree? Clear? Okay, so not smooth at uv equals 0, 0. Okay, clear? Okay, so this is the first step. Parametrizing surfaces. We're going to see many more examples as we move along, but this is the first step. The next step is, again, in accordance to what we did with curves, the next step is, how do we find the area of a surface? Okay? How do we find the length of a curve? How do we find the area of a surface? That's the next clip.